This video is Module 12, IPv6 addressing for the Cisco Networking Academy. We're going to be looking at these topic objectives in Module 12. Explain the need for V6 addressing. Why do we need it if we have V4? IPv6 address representation. IPv6 address types. We're going to be looking at GUI and LLA static configuration, and GUI in this case is not graphical user interface. It is the global unicast address. And we're going to be looking at the dynamic addressing for V6 GUIs. We'll also be looking at dynamic addressing for V6 LLAs, V6 multicast addresses, and subnetting of V6 network. This video is going to be a little bit longer. I decided not to break it into two because the material didn't warrant enough to break it into two videos, but it's going to be a longer video, so probably closer to 30 minutes. So you can fast forward it, you can pause it wherever you need to, and as always, I'll have the closed caption on there. So what has brought us to needing V6? V4 had some issues. It was created back in the early days of networking. We started running out of V4 addresses early on, and V6 was created in 1995, and ever since then we've been implementing it. V4 and V6 do coexist. They will coexist into the near future, and the transition will take several more years. I don't know what that date is when we will no longer use V4. It's going to be a long time. All new equipment comes with V6, but the migration techniques can be divided into three different categories. Dual stack. The device runs both V4 and V6 protocols stacked simultaneously. My computer runs both stacks. It runs V4 and V6. My cell phone runs both of them. You have tunneling. That's a method of transporting a V6 packet over a V4 network. The V6 packet is encapsulated inside the V4 packet, so the V4 device doesn't see that V6 address. It just takes those packets and passes them along, and when it gets to the other end, it gets de-encapsulated or unencapsulated, and then the network devices on the other side can read that V6 address. And then we have translation. Network Address Translation 64, or NAT64, allows V6-enabled devices to communicate with V4-enabled devices using a translation technique similar to NAT for V4. So how do we represent V6? V6 addresses are 128 bits in length. V4 was 32. This is 128. They are written in hexadecimal. I recommend that you go read up a little bit on hexadecimal. This video doesn't cover how to read in hexadecimal and how to look up hexadecimal numbers and how to convert hexadecimal numbers. However, there are lots of videos and resources out on the internet for that. I recommend you go and check that out. I'll put a link in the description below to the Wikipedia page on hexadecimal so you can get a head start on finding that. V6 addresses are not case sensitive, and they can be written in either lowercase or uppercase. They are not case sensitive. The preferred format, and we have different formats, by the way. When we say preferred format, that's where everything is written out. And here it's represented by X's and colons. Each X consists of 4 hexadecimal values. In V6, we call it a hextet. A hextet. Hextet. It's the unofficial term used to refer to the segment of 16 bits or 4 hexadecimal values. So here's a couple of examples of V6 addresses in what we call the preferred format. This is where everything is written out. This one here we have 2001:0db8, and that's not just a number. That's actually in hexadecimal. So that if you convert that to hexadecimal, you can convert that to a binary number, or you can convert it to a decimal number. But 2001 is not a decimal number. That is a hexadecimal number, just so you know. So 0000, 111, 0000, and then colon, 0200. Now that's what we call the preferred method of when you write it out. However, you can collapse these. And there's rules to do that. There's some rules to collapse those or to make it easier. The first rule to help reduce notation, so you don't have to write that whole entire V6 address out every time, is to omit. I'm going to say that right. Leave out. That's a better way to say it. Leave out any leading zeros. For example, 01AB can be represented as 1AB. That's pretty cool, but that's a leading zero. You cannot eliminate the trailing zeros or zeros in the middle. It can only be it can only be leading zeros. So this one here can be A00, this one can be AB. And you know, based on that rule, that if you see an AB in a hextet, that it's 00AB. That's why we have that rule, so you know what it is. The rule only applies to leading zeros, not to trailing zeros. Otherwise, the address would be what we call ambiguous. We wouldn't know where the zeros go. So this is a preferred method here down at the bottom, and this is a no leading zeros. This is where we could write it out and we could say, okay, we're gonna take out all the leading zeros, and you can see how it's much smaller now. It's much easier to write. And if you wrote it into a system this way, if you were to put this into your router or your switch, it would still take it because the device knows what the rules are. A double colon, this is rule 2, a double colon can replace any single contiguous or side-by-side string of one or more 16-bit hextets consisting of all zeros. That's a lot to say. Simply meaning that if zeros are beside each other, we can eliminate them. But they have to be beside each other. We can't eliminate some zeros here and not zeros in another place. So the double colon can only be used once with an address. You can't do double colons somewhere else because then we won't know where all the zeros are. So when we look at this preferred format, we write it out the long way. The compressed way is get rid of our leading zeros, and we can collapse any zero hextets that are beside each other. So an example here, we can take these 3 out. And when we look at this, we see 1, 2, 3, 4, 5 hextets, right? And there's 1, 2, 3, 4, 5, 6, 7, 8 total. So we know that we're missing 3 hextets in there of zeros. And any device that we write this into would also know that. And we also have trailing zeros are gone. So now we have what we call a compressed version. This is a much easier way to write a v6 address. And I don't know if I would remember that off the top of my head, but it's a much easier way to write it down versus the preferred way. Just remember those rules. Leading zeros and zeros or hextets beside each other, that they have to be beside each other, can be compressed down to a double colon. Now we're going to look at v6 address types. We have unicast, multicast, and anycast. If you remember back to the v4, we had some different types, but here we're calling there's a couple of things that are different. The name we use for them. There's 3 broad categories of v6 addresses. The first one is unicast. Unicast uniquely identifies an interface on a v6 enabled device. Multicast is used to send a single v6 packet to multiple destinations, very much like v4. And anycast, this is the difference. Anycast, this is a v6 unicast address that can be assigned to multiple devices. A packet sent to an anycast address is routed to the nearest device having that address. So unlike v4, v6 does not have a broadcast address. However, there is a v6 all nodes multicast address that essentially gives you the same result. v6 prefix length, it is represented in slash notation, and it's used to indicate the network portion of a v6 address. Remember with v4, we had our network portion and our host portion. The same thing applies to v6. The v6 prefix length can range anywhere from 0 to 128. The recommended v6 prefix length for LANs and most other types of networks is /64. Now that's current times. This is 2020. 10 years down the road, it may be different. 20 years down the road, it may be different. But for now, the recommended length is /64. So what we're doing is we have our prefix of 64 bits and our interface ID of 64 bits. And we know that our interface ID, or our host portion, is 64 bits because we have a /64 there. It's strongly recommended to use a 64-bit interface ID for most networks. That's because stateless address auto configuration, or SLAAC, SLAAC, which is covered in other modules. It's not covered in this module. It uses 64 bits for the interface ID. It also makes subnetting easier to create and manage. Let's take a look at unicast addresses. v4 devices that have only a single address. v6 addresses typically have 2 unicast addresses. We have a GUI and an LLA. The GUI is Global Unicast Address, and I call it GUI. Somebody else might call it different, but I call it GUI for short. This is similar to the public v4 address. These are globally unique internet routable addresses, so everybody on the internet can see them. Then we have the link local addresses, or LLA. That's required for every v6 enabled device, and it's used to communicate with other devices on the same local length. Think of local area network. LLAs are not routable and are confined to a single link, single local area network. Now there's a note about the unique local address. v6 unique local addresses range from FC00::7 to FD FF://7. They have some similarity to RFC 1918 private addressing that you reviewed or should know from v4, but there are some significant differences as well. Unique local addresses are used for local addressing within a site or between a limited number of sites. Think local area network. Unique local addresses can be used for devices that will never need access to another network. They're all contained, self-contained inside. And unique local addresses are not globally routed or translated to a global v6 address. Now, many sites use the private nature of RFC 1918 address to attempt to secure or hide their network from potential security risk, and that was never an intended use of the ULAs. That was never an intended use, but some organizations do use that because then, since those v6 addresses are not routed, they don't get out, so someone would still have to come through your router to get into your network versus having an IP address internally there. v6 GUI, or GUA, global unicast addresses, they're globally unique and routable to the v6 internet. Currently, only GUIs with the first 3 bits of 000 or 2000:/3 are being assigned. Currently available GUIs begin with a decimal 2 or a 3, and that's only 1/8 of the total available v6 address space that's out there. So we're not even begun yet to pass out all the v6 addresses. The GUA structure, global routing prefix. The global routing prefix is the prefix or network portion of the address that is assigned by the provider, such as your ISP to a customer or to a site. The global routing prefix will vary depending on ISP policies, so they may break it up a little bit when the ISP gets their breakdown of the v6 address. They may break it down further a little bit. It's up to them, and then they'll pass it out to their customers. Then we have our subnet ID. That's the area between the global routing prefix and the interface ID. The subnet ID is used by an organization to identify subnets within its site. And then we have the interface ID. That is the ID. It's equivalent to the host portion of a v4 address. It's strongly recommended that in most cases /64 subnets be used, which creates a 64-bit interface ID. Now, there's a note that v6 allows the all zeros and all ones host addresses can be assigned to a device. The all zero address is reserved as a subnet router anycast address and should only be assigned to routers, just as a note there. v6 LLA. A v6 link local address enables a device to communicate with other v6 enabled devices on the same link and only on that link or subnet. Packets with the source or destination LLA cannot be routed. Every v6 enabled network interface must have an LLA. And if an LLA is not configured manually on an interface, the device will automatically create one. And they are in the range of FE80::/10. Here's an example here. They're going to be maintained locally. GUI and LLA static configuration. Most v6 configuration and verification commands in the Cisco IOS are similar to their v4 counterparts. In many cases, the only difference is the use of IPv6 in place of the IP within the commands. We have an example down here. We put an interface gigabit Ethernet 0/0/0. We put in IPv6 space address space, and then we type in our v6 address, and in this case it's a compressed 2001:DB8:ACAD:1:1, which remember our hextets would be in there, /64. We put no shutdown to bring the line up. We type exit, and now we have a v6 address on that line. In a Windows host, you can manually configure a v6 address. You would just go into a Windows, go into the TCP/IP v6 properties, type in the v6, type in your /64, put in your default gateway, and then of course we're not setting DNS here, but you can also obtain it automatically from a server. When DHCP v6 or SLAAC is used, the LLA of the router will automatically be specified as the default gateway address. That'll be set up in the DHCP or the SLAAC commands. Static GUI configuration of a link local unicast address. Configuring the LLA manually lets you create an address that is recognizable and easy to remember. LLAs can be configured manually using the IPv6 address and then your v6 address. Link local command. So IPv6 address, put in your v6 address, put in link local command, and that sets it as a link local. So this example shows configuring. We go into our interface gigabit Ethernet 0/0/0, IPv6 space address space, we put in our v6 address, space link -local, no shutdown and exit. And the same LLA can be configured on each link as long as it's unique on that link. Common practice is to create a different LLA on each interface of the router to make it easy to identify the router and specific interface. In other words, you're going to say that, this one would be FE8011, FE802131, and so forth. Dynamic addressing for v6 GUIs. You have RS and RA messages. Devices obtain GUI addresses dynamically through Internet Control Message Protocol. I didn't say that right. Internet Control Message Protocol, ICMP, version 6. ICMP version 6. Router solicitation. Remember we had ARP under v4? Well, this is v6. Router solicitation, or RS messages, are sent by the host device to discover v6 routers. Router advertisement, or an RA, are messages that are sent by the routers to inform host on how to obtain a v6 GUA and provide useful network information such as network prefix, prefix length, default gateway address, DNS addresses and domain names. The router solicitation can provide 3 methods for configuring a v6 GUI. You can do SLAAC, SLAAC, SLAAC with stateless DHCP v6 server, or stateful DHCP v6 with no SLAAC. Method 1, SLAAC, allows a device to configure a GUI without the services of a DHCP server. Devices obtain the necessary information to configure a GUI from the ICMP v6 RA, and the prefix is provided by the RA, and the device either uses the Let me say that again. It uses either the EUI64 or random generation method to generate an interface ID. So it would look something like this. We'd get a prefix of 2001, :DB8, :ACAD, :1, and then we'd see our FC99. It'd be generated on the host side. Method 2, an RA can instruct a device to use both SLAAC and stateless DHCP v6. The RA message suggests the device use the following: SLAAC to create its own v6 GUI, and the router LLA, which is the RA source v6 address, as the default gateway address. Kind of neat. A stateless DHCP v6 server to obtain other information such as DNS server address and a domain name. So it's going to use a combination of those two. And method 3, this is stateful DHCP v6. An RA can instruct the device to use stateful v6 only, so no SLAAC. Stateful v6 DHCP v6 is similar to DHCP for v4. A device can automatically receive a GUA and the address and the DNS servers from the stateful DHCP v6 server. The RA message suggests devices use the following: the router LLA, which is the RA source for the default gateway. And finally, a stateful DHCP v6 server to obtain a GUI, DNS server address, domain name, and any other necessary information. EUI64 process versus randomly generated. When the RA message is either SLAAC or SLAAC with stateless DHCP's v6, the client must generate its own interface ID, and the interface ID can be created using the EUI64 process or a randomly generated 64-bit number. The IEEE define the extended unique identifier or modified EUI64 process, which performs the following: a 16-bit value of FFFE in hexadecimal is inserted into the middle of the 48-bit Ethernet MAC address of the client, and the 7th bit of the client MAC address is reversed from binary 0 to 1. So what that's going to do is that's going to be a semi-random number, or number that's not going to be used by something. It's going to take a lot to get the same number on your same network, because when you insert that value in from the MAC address, MAC addresses are supposed to be unique. Unless you're spoofing a MAC address, it should be unique. And then taking the 7th bit of the client MAC address and reversing it from 0 to 1 makes it even more unique. And so the 48-bit MAC gets this applied to it. And that can become what I call a semi-random EUI64 interface ID. Randomly generated interface IDs. Depending upon the operating system, a device may use a randomly generated ID instead of using the MAC address and the EUI64 process. So with Windows Vista, Windows uses a randomly generated interface ID. So leave it to Microsoft to do it different, which is fine. But if you go into your Windows and do your ipconfig, you can see your v6 address here. This one was randomly generated. And then you've got your link local IPv6 address and then your default gateway. Now, to ensure the uniqueness of any v6 address, the client may use a process known as duplicate address detection, or DAD. This is similar to an ARP request for its own address. If there's no reply, then the address is unique. So it'll do a DAD request. Is anybody else out there with the same address? If not, it'll go ahead and use it. Dynamic addressing for v6 LLAs. All v6 interfaces must have a v6 LLA. So like v6 GUIs, LLAs can be configured dynamically. And this figure below shows the LLA dynamically created using the FE80::/10 prefix and the interface ID using the EUI64 process, or a randomly generated number. So we get the FE80::/10, and then on the back side for our interface ID, we get a randomly generated number. Operating systems such as Windows will typically use the same method for both a Slack-generated GUI and a dynamically assigned LLA. So here we have the EUI64 being generated, and then a randomly generated. Dynamic LLAs on a Cisco router, they automatically create a v6 LLA whenever a GUI is assigned to the interface. By default, Cisco iOS routers use the EUI64 to generate the interface ID for all LLAs on v6 interfaces. And this is an example below. We do the show interface gigabit Ethernet 0/0/0. We see that the line is up, the protocol is up, it gives us our hardware information, and then we see our and then we do the show IPv6 interface brief, and then we get our numbers down here. The v6 multicast addresses. v6 multicast addresses have the prefix of FF00::/8. There's two types of v6 multicast addresses: well-known multicast addresses and solicited node multicast addresses. Multicast addresses can only be destination addresses and not source addresses. Well-known v6 multicast addresses are assigned and are reserved for predefined groups of devices. There's two common v6 assigned multicast groups. All nodes multicast group. That one is the multicast group that all v6 enabled devices join. A packet sent to the group is received and processed by all v6 interfaces on a link or network. And then we have all routers multicast group. That's a multicast group that all v6 routers join. A router becomes a member of that group when it's enabled as a v6 router with the v6 unicast routing global configuration command. Solicited node v6 multicast. A solicited node multicast address is similar to the all nodes multicast address. It's mapped to a special Ethernet multicast address, and the Ethernet NIC can filter the frame by examining the destination MAC address without sending it to the v6 process to see if the device is integrated target of the v6 packet. Now let's take a look at subnetting a v6 network. It's not as difficult as v4 subnetting, and it looks difficult. When I first started trying to learn how to subnet a v6 address, it looked really, really hard because I was used to v4, but once you get used to it, it's actually a lot easier than v4. So v6 was designed with subnetting in mind. Not unlike, v4 was not. A separate subnet ID field in the v6 GUI is used to create subnets, and the subnet ID field is the area between the global routing prefix and the interface ID. So you have three parts: your global routing prefix, your subnet ID, and your interface ID. Given the 2001 DBE ACAD::/48 global routing prefix with a 16-bit subnet ID, we can get increments to the subnet ID to create 65,536 subnets out of that one number. So it allows 65,536 subnets within there. So the global routing prefix is the same for all subnets. So we get the same global routing, 2001:DB8:ACAD, and then we just take our subnetting ID and we just increment it by one, all the way up to 65,536. Subnet allocation, the example topology below, requires 5 subnets. So we need 1, 2, 3, 4. We're gonna do 5. No, we're gonna do 5. Yeah, we're doing a VLAN here, a VLAN here, a VLAN here, a VLAN here, and one in here. So 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, whichever way it works. On the example here, it looks like that. So the 5 v6 subnets were allocated, and we just gave them 0001, 0002, all the way up to the 6, and we could keep going. But the 5 subnets allocated for 65,536 available or given right here. When we configure a router with v6, The example below shows that we do our interface gigabit Ethernet, IPv6 address. We put in our address /64, do the no shutdown to bring the line up. We can set our interface gigabit there, 001. And if we notice here, this one's ACAD 1, this one's ACAD 2, and this one's ACAD 3. So we set all 3 gigabit Ethernet connections with separate subnets. So what did we cover in this module? We covered a lot. And don't get discouraged with V6. It looks intimidating if you've never done it before, if you've never worked with it before, if you've never used it before. I encourage you to look back over this module, go into the material in the course. I also encourage you to check out the V6 Wikipedia page. It is very complicated, and V6 can be complicated, but for what you're learning in this course, don't let it scare you. It is easy to learn if you just take it baby steps, and you'll get there. So we've ran out of V4 addresses. That's what we learned. V6 addresses are 128 bits in length. We have 3 different ways of writing them: the preferred way, or removing the leading zeros, or compressing them all together. Just remember those rules. That's the important thing to remember. Remember your GUIs and your LLAs. Remember when you're setting subnetting, and I'm just going to jump on down here, that when we're subnetting we subnet in the subnet ID, and there's 2 different types of V6 multicast addresses, and we have the different types, the multicast, unicast, and the anycast. All right, I hope this information was helpful for you. I hope this video series is helpful for you as well, and I hope you have a great day. Stay safe, and remember to be excellent to each other.